is given by Professor Antonio Rivera from the Institute of Nuclear Fusion, Guillermo Velarde, and also professor of the Department of Engineering, Energetic in the College of Industrial Engineering. Antonio, together with Raquel, were my two great incorporation to the Institute in the last years, since a lot of years now, but that too great. They changed very much the life of the Institute from the point of view of the knowledge of material, much more deep than before, and the experimental part. In particular, Antonio is a specialist in nanoplasmonic. He will not talk today, and he will talk about how nanotechnology can provide solution in general to the fusion technology, and in particular to the design of the first wall of the different reactors. So, Antonio, you can start.
¿Se oye, no? ¿Se oye bien? Okay. Okay. Thank you, Manolo. Nice to see so many colleagues and friends and students, the good ones I had this year. The rest are on the beach, probably. Yeah, it's good. I'm not assuming I know you are all tired. I was tired myself. So, but this is going to be soft, not a nuclear physics lecture, I think. And I'm going to speak about materials as Joaquin, as Raquel, Angel, many people, trying to emphasize the importance of the materials. Even Mike Tobin was trying to escape from the materials with his approach. That probably is a good idea, the best option. Okay, but I'm going to speak about solutions. Once we know all the problems related to irradiation, okay, from time to time you have an idea, kind of crazy idea, and then it turns out it moves to a lot of simulations, and then maybe to a prototype for experiments, a test module or something like that, which is quite nice when you are involved. So young engineers would really enjoy that. Okay, I will show that now. So first, since this is a course, I'm going to give a short introduction about this I was discussing right now. And then I will show our last proposal to solve an unsolved problem so far. And it's related to Mike's question right now. So I will go through that. So first, this small introduction. Something happens, escape. Okay, so first of all, in both approaches, either laser fusion or magnetic fusion, we see that irradiation is the main concern, okay? So in laser fusion, we inject targets into a chamber that can be evacuated. It can have wetted walls. It can contain a gas, many options. But okay, once the target explodes, irradiation is a concern. And in magnetic fusion, we see a neater sketch there. We have a plasma that is continuously producing irradiation. First of all, neutrons, but also ions that mainly touch the first wall and go to the divertor. Just to visualize this, I have an animation and a real movie. The animation is about inertial fusion. Simply, but very simple. The target is compressed, ready for explosion, explodes, and you get neutrons, ions, X-rays, and we will see the spectrum right now. And then when we speak about magnetic fusion, this is a movie made with thermographic camera in jet. So what you see is very hot, the divertor region, because the plasma is being continuously discharged over there. But in addition, from time to time, several times per second, in most tokamaks, you have edge-localized modes. So these pulsed events are very important because during these pulsed events, the load you put into the divertor is really huge. Okay, so this is a sketch of a laser fusion power plant. And basically, all the materials involved there are constitute or are influenced by irradiation. If we speak about the first wall, kind of refractory material like tungsten, is basically affected by X-rays in case of indirect drive plants, or ion pulses in case of direct drive plants. Then the structural material is mainly affected by neutrons to the extent that it can last something like 1 year. Regular steels cannot last much more. And then the final lenses, in the case of laser fusion, receive neutron irradiation and ion irradiation and X-ray irradiation. We can try to mitigate, and we have to mitigate the ion arrival, but we cannot avoid the arrival of neutrons, and it's an important point. Okay, as an example, I will put one transparency about that related to our work we did a few years ago, and then I go to the first wall. And that is this. Okay, I said now, the lenses are subject to ion irradiation, X-ray irradiation, and neutron irradiation, to the extent that we assume we will be able to mitigate the arrival of ions with some kind of electrostatic divertor or whatever, okay? But neutrons will reach the lens. This is the real lens proposed for a hyper project, that is the Laser Fusion European project, okay? And it's realistic. There are squares of 60 by 60 centimeters, and we realized that the temperature profile on the lens will not be uniform, just due to the neutrons. And that is tremendous, because if you think it carefully, that changes the density. Okay, the gradient can be near 200K. So the density of the lens changes, the refractive index changes, and then K and 3000K. Okay, so that is promising and allows us to go further with this. If I go to a magnetic fusion scenario, and this is ITER, then the situation is quite extreme. I'm estimating what you can find in literature. This is, well, there are many other approaches, but consider anyway that ITER is not a power plant. It's not a power plant. Yeah, it's an experimental facility. And anyway, the edge-localized modes can be very dangerous to the extent that in this case, according to these simple calculations, we can easily exceed the melting point. Area divertors, something like that. In that case, okay, we still can get a temperature lower than the melting point if we go for tungsten divertors. Okay, anyway, we see that in some cases, in some scenarios, the temperature will not reach the melting point. So we go further. Now, what happens to the nanoparticles? These are atomistic simulations, molecular dynamics. And what we did is we took a tungsten nanosphere. We had experience with this from other materials like palladium, nickel, and gold, okay, and silver. And in this case, we used also tungsten, okay? And then we were introducing helium, let's say, in a hard way, yeah? 1,000 helium atoms every time. We were putting that at 3,000 K, and then at a certain moment, the nanoparticle explodes. If you see this, you think, wow, this is a terrible idea, right? You want to keep helium there, and it's not working. Well, I anticipate the conclusions. This is similar to the magnetic fusion scenario. Why? Because when you have plasma discharge, the ions have low energy. So basically, all of them remain in the first monolayer of nanoparticles, according to our simulations. If you are in laser fusion, the ions have a significant energy. Remember, helium has, on average, 2 megaelectron-volt. And deuterium and tritium, on average, has 300 kiloelectron-volt. That means that they penetrate really far, really deep into the material. So every nanoparticle in inertial fusion conditions receives, on average, a few ions per shot. Whereas in magnetic fusion, every nanoparticle from the first layer receives thousands of ions in every discharge. Yeah? I'm considering an edge-localized mode discharge. Well, but the interesting thing is, okay, let's study in more detail what happens with the temperature. We did molecular dynamic simulations, and then you have those 4 cases that correspond to different temperatures, okay, in the plot you have on top. It's incredible how resistant these particles are. Number 3 corresponds to 3,500 K, and still the nanoparticle is preserved, and the cavity is preserved. If we put gas inside, the nanoparticles, the nanospheres, are even more resistant. So this is quite nice. Okay, the nanoparticles are really resistant, incredibly resistant. They look like tiny things, tiny objects, not very resistant, but actually they are. Well, the referee asked us to show what happens when you cycle this. And well, from the point of view of the atomistic simulations, nothing can happen because the potential energy is not changing. So we did several cycles. We subjected these nanoparticles to different cycles, and what we observed is some reorganization of atoms on the surface, but basically nothing changes. We can really cycle this. So in principle, the nanoparticles will resist different cycles, and that makes us think that they can resist quite long times. But now, this is the interesting thing. What happens when you pressurize? I anticipated before. Depending on the temperature, the nanoparticles suffer some rupture process at different pressures. For example, at 3,000 K, the nanoparticles resist an incredible value of 5.5 gigapascal. It's really incredible. But at certain point, you have a rupture point, and the nanoparticle breaks. Okay, when we saw that, we were a bit disappointed, considering, okay, what is the lifetime, how many cycles can they resist? But then we found out the following. If you inject gas in a gentle way, as in laser fusion, a few ions per cycle, then what you observe is a hole, pressure release, and the hole closes itself in a very short time. Compatible with the temperature, with the time duration, the nanoparticles are hot. Well, this is quite incredible. We knew that the nanoparticles are very resistant, and they tend to this stable shape. But we didn't expect that. And this is really promising. We call it a self-healing mechanism. So pressure is, this is atomistic simulations, but in this we know by experience that they reproduce quite well the reality in these situations. Okay, the point is, okay, so if we inject a few atoms inside, an opening will appear, pressure is relieved, and then it will close. Okay, fine. Self-healing mechanism. So we thought, okay, we have to go, I'm finishing, we have to go to the ultimate problem, defects. If everything works, still we have a problem with defects, okay? And then we have object kinetic Monte Carlo for that works quite fine. So we can put defects on the shell, and we can put ions inside the cavity, and then we see something like this. This is an animation in which you see the defects we introduce and how they develop in time. And you see that, okay? They annihilate with each other, interstitials and vacancies, and they anneal out when they reach the surfaces, the outer or inner surface. Well, it's quite okay, and it's expected, actually, because the shell thickness is smaller than the mean free path of the defects. So they can really travel to the surface and anneal out, disappear. Okay, we took extreme conditions in laser fusion. This is more than we expected, and we observed that we put the defects there, in this case only vacancies, and after 3 microseconds, giving the right ramp we expect, the ramp temperature we calculated with the heat equation, and then we observed that the defects disappear. So this was the main problem. This is the main problem with bulk material. They do not disappear. They cannot escape. They cannot go anywhere. And once helium is trapped there, remain, let's say, forever, because you almost have to melt the sample to make helium escape. This is what we call the self-healing mechanism 2, second healing mechanism. And it's so efficient that even in the case of magnetic fusion, it works. I said before, okay, magnetic fusion will not work because the ions are injected in the first monolayer of nanoparticles because they have low energy, so the nanoparticle will explode. The self-healing mechanism 1 will not work. But anyway, we tried to put all the defects we expect in that situation, and you see that it's quite complex because we have clusters now. We have clusters of interstitials, clusters of vacancies in different colors, combined with helium. And anyway, when we heat up for enough time, for a realistic time, all the defects disappear. So let's say this self-healing mechanism, as expected, by the way, is very efficient because the shell thickness is very small. Okay? So I conclude with this, following conclusions. This is a novel proposal for first world material, since we don't have a solution, okay? This could be a solution that may be interesting to work on that. And it's based on the superior properties of nanoparticles in some cases, okay? And it's interesting to work with the gas content of the nanoparticles, because if gas stops the incoming ions, that is for free, let's say. It's not damaging the materials. Now, the nanoparticles we show that can withstand very high temperatures and pressures, and we observe two self-healing mechanisms. The first one works only in laser fusion conditions when a few ions reach the nanoparticles per shot. Yeah, in these soft conditions, an opening appears, pressure is released, and then the opening closes. And the second self-healing mechanism is related to the mean free path of defects that is larger than the shell thickness. So annealing is very efficient and defects disappear. In magnetic fusion, the idea cannot work because self-healing mechanism 1 will not work, but is promising for the prototype scenario. Yeah? So this brings, we put in the paper that maybe the idea is to go to, when you have to deal with first world problems, maybe it's a good idea to have low yield targets, yeah, to go to something related to laser fusion. This is similar to the idea, to the trend now to go to modular reactors. Do it small, and maybe you gain something. Less power, but okay, put more reactors for even cheaper price. And okay, for a practical realization, we need further work. For example, how to prepare the first wall, putting layers of nanoparticles. By the way, there are papers about that with gold nanoparticles, so that could be used. We can use foams, for example, nanofoams with closed porosity. And what about the gas? We don't know much about the gas, especially the thermal conductivity, but that can be part of a future work of any of you, new generations. Okay, that's all. Thank you.
Again, really very good, Antonio. Great talk. I am enjoying these 2 days very much. I am learning. Wow, you cannot imagine, my friend. Great talk, really. You can imagine this kind of mechanism that if this is true, that they could make nanoparticles in different conditions could be filled with gases, and they open depending on the pressure in other part of the of the system, and they release the gases. I'm not talking only about fusion. Not talking about fusion, but believe in that. So you catch gases, and in a different condition in your in your system, under different conditions of pressure, they deliver gases.
In
So
medicine,
that's fantastic.
Medicine to deliver
Medicine, many different situations. It's really, I mean, we need to make experiments of that, certainly, Antonio. We need to make experiments of that. Yeah, I want that you talk to these people about other aspects that you could not talk of everything that you did on optics with the video in changing the properties of the materials, the silica.
Waveguides. We did waveguides as well.
Yes, waveguides. Yes, I want you to talk about that because it's also a little bit. Just a comment.
Oh, no, if you irradiate, for example, with heavy ions, there's a patent, by the way. You can you change the refractive index. It's funny. Even one single track has a different refractive index because the density changes. So if you accumulate many tracks, they overlap, and you can form a continuous layer. Raquel showed something. For that reason, you saw interference. Maybe you didn't realize. But when she showed the reflection spectrum, you saw interferences at high fluence. And that's because a layer was formed. So the light reflected on the surface and on the interface. And then an interference pattern appeared. And it's an ambiguous proof of layer formation. Of course, we saw the layer with Raman and other techniques. But that is funny. It's funny to produce.
Well, not only fun, but you did not talk, and I will talk because you don't did. I do. These guys make experiments with Luis Bañares in the UCM using nanoparticles, spherical nanoparticles. They made with laser, no? Or they irradiate with ions on in situ, everything. They change the shape of the nanoparticles. Correct me if I am wrong. They change the shape of the nanoparticles, and the absorption line of the optics, this is what I wanted to say, change drastically. They can really tailor the absorption line of the optical material with the irradiation of the nanoparticles by ions, changing the shape and the elongation of the nanoparticles.
Yeah, well,
that's really great.
I will only say one word about this. The interesting thing about going now to plasmonics and the radiation is that we're using the methods we are using in nuclear fusion, because nobody is using plasmonics and irradiation. I mean, applications do not occur under radiation. We are alive, yeah? And most applications do not have irradiation around. But if you irradiate nanoparticles, for example, and then you have a very high electronic excitation, then we can use methods that we applied first in nuclear fusion. And that is funny now, to go to plasmonics from nuclear fusion.
Do you have any question? You have an excellent occasion to talk one of the really key person in nanoplasmonic and all this aspect from nanotechnologies materials. No? Well then, oh yeah, Javier, please. No, wait, because the streaming.
It's a very naive question. As you say in your conclusions, you say that it's a very radiation-resistant possible solution. And I told you it's very naive. Neutrons has something to do in all this evolution of this, especially because you know that in inertial fusion, the peak of the neutrons when reach the first wall can be extremely high.
Yeah, but when you compare with ions, it's very little, really.
No, because I remember when Manolo...
Because imagine 25% of the energy in a few microns, okay? The remaining is still 70% or something like that. But it's deposited in many centimeters. That gives you the idea of the influence of ions in the first wall versus neutrons.
Yeah,
it's 25% of the energy in microns.
I understand.
Versus the remaining in many centimeters.
Yeah, my point is that the only thing is that...
we consider that, by the way. When I said before that in this case we went to extreme cases, we put we assume, okay, a neutron came here, we put more defects than expected, And in addition, we put ions, more than expected. It's so resistant, we saw this case, that in this case, okay, even if a neutron comes around and produces some defects, the defects will annihilate out.
Oh, I understand. Yes, it's only from the, let me say, docential point of view is that we always say energy is deposited in some amount of energy, but important is not that amount of energy that is deposited. It's the force of the energy that is deposited. I mean, the mechanism that can give rise this energy. The mechanism of damage for neutrons are different than the mechanism of damage than sharp particles.
Yeah,
right.
Neutrons generate, neutrons transmit a lot of, they don't interact or they interact producing very, you should know, very energetic primary knock-on atom, we call pKa. And that has consequences because that produces cascades of damage. Yeah? But as I showed here, even better here, this is very efficient in annealing out these defects.
Thank you, Antonio. In fact, what's more a question, more for the student than for you, in order they can think about that.
Good. Remember that you all have an examination from Javier. Javier did an examination for you. Okay, so if there are no more questions, we are here